It's gonna make another one.
Okay, I'm just gonna talk very loud and hope that actually gets on the recording.
So when I was.
Oh yeah, I don't know what else to do.
When I was
How can I help? Yes, it is. This is your time. This is whatever you want it to be. Problem. We got.
Step on tragic. We already done homework?
Yeah.
I finished it.
I've been annoying. Run this homework.
Yeah, how do you do the homework?
That's, you get the homework done?
I had the biggest epiphany today. Realize.
Everyone there? Okay. We have a case where this is launched from a spring. And then it goes up a little hill, over a rough spot, around a loop-de-loop, and then woo! You get to ride it once. And it comes down. And we want to know what that, the first thing we want to know is what's the coefficient of kinetic friction for that rough patch? Now, we ask, is this a collision? No, that comes much later when you hit the ground. Is time involved? No. So that leaves this as an energy problem. So we're going to start with the energy equation. It's this, we got energy in the morning is equal to energy at night, except when it's not, and it's definitely not in this case, because there's work being done by that friction force. Now, if I look at this situation, I need to decide, and I get to decide what I mean by initial and final. Well, I'm looking for something that happens in the middle. So I better know what the energy is at my initial state and what it is at the final state. Well, I know what the energy is at A, and I know what the energy is at B. So I'm going to make those my initial and final. And then at each of those, I ask the same three questions. Is anything with mass moving at A? No. Is anything up off the floor? No. Are any springs stretched or compressed? Yes. So I have 1/2 K delta S squared, and you'll need to have that formula memorized. And then I go to B, and I ask the same questions. Is anything with mass moving? Yes. Is anything up off the floor? Yes. Are any springs stretched or compressed? No, not anymore. So I go back and I write this as 1/2 mv at B squared plus mgh at B. Now in between there was negative work done by the friction force over some distance. Now, folks, that's the physics. That's all there is to an energy problem. That's all the physics. What comes after this is just algebra. So let's do the algebra. What do we know here? We know that K is 30,000. We know that delta S is 2 meters. Remember to square that. The friction force depends on the normal force. And so that's going to be mu sub K times the normal force. Well, if I have a mass of 250 kilograms, the normal force is going to be 10 times that, or 2,500 newtons, and the delta X is 2.5 meters. And that's equal to 1/2 times the 250 kilograms times the speed at B. Well, it's going 12 meters per second. Remember to square that. And then I've got 250 kilograms times 10 newtons for each kilogram times. Now here's where people made mistakes when this was on an exam. Yes,
Can you show us your work?
like that?
Yeah.
Okay, sorry. Was I talking for a long time without you seeing what I was doing? Okay, I'll go back. There's the spring constant, stretch, compression, the mu sub k, the normal force, that distance that it was traveling, the mass times the speed squared, the mass times g, and now where people made their mistake was they took the radius and doubled it to get 8 meters, but they forgot to add the 2 meters at the bottom. And so the total there is going to be 10 meters. Okay. Now, I'm going to that's just not going to work. You got to be 10% smarter than it. Okay, so now we just plug in. So this is going to be 60,000. That's going to be joules minus mu sub k times 2.5 times. Okay, we got 0.5 times 6250, and that's equal to 2,000 plus 25,000 joules. Okay, so like I said, this is just math now. I'm going to bring this over here and all of this over here. So I have 60,000 joules minus 43,000 joules is equal to mu sub k times 6250. And just, can you divide? Is that? So is the rest of the problem something you're concerned about, or was it that's the hardest part of the problem?
I think I got that.
Well, you
this
got
is
that part.
Part B, the normal force,
Oh, yeah.
is that just the weight?
No.
Net force.
No. That's why that problem in there is so that you would see that it's not the weight. Okay, so if it's going around that track, the track's up here, and the cart with the people is down there. So the normal force by the track on the cart is going to be a push by something on top onto something on bottom. So that's going to be a push. If I were to draw the free body diagram, I would have the weight force on the cart, then I would have this normal force by the track on the car. Well, that doesn't look balanced. That doesn't look balanced at all. And it shouldn't, because remember, right before the last exam, we made a big deal about going into the exam and looking for anything that's going in a circle. And if it's going in a circle, you draw an arrow towards the center of the circle and label that centripetal acceleration. And that's going to be E squared over R, which in this case is 12 squared over 4. And that's going to be 36 meters per second squared. Now, I know that this diagram has to scream this acceleration. Well, how loud should it scream? Well, that's always given by F net equals MA. That's going to be 250 kilograms times 36 meters per second squared down. And that's going to be, can't do that in my head, 9,000 newtons down. Well, I know that this weight force is 2,500. And I got to have a total of 9,000. So this has to be 6,500. Yeah, you always want to look for things that are going in a circle. And as I said in lecture, the fact that these frictionless cracks do no Verk mean that we can put very complicated looking carnival rides in the exam, making it look really hard, but it's not really, because you don't get robbed. It doesn't change the energy at all. And that allows us to do these loop-to-loop problems. We can come back and review circular motion. Yes.
Can you go over impulse and like when to use it and how you know when to use it?
So impulse is what changes momentum in much the same way that work, or Verk we call it, changes energy. And so you ask yourself, is the momentum changing? For example, if I slam on the brake and I slide across the pavement, well, I had a lot of momentum. I was going fast, and then I don't. Well, clearly something changed it. And if I want to figure out how far the car slid, well, that's energy. I start with a certain amount of energy. I get robbed by Verk, negative Verk, and then I got nothing. But if I want to know how much time it took to stop as I was scraping across the pavement, that's momentum. And I figure out how much momentum I had. Then I figure out how much impulse, negative impulse happened, force times time. And then it gets to 0. But ultimately, an impulse is just a fancy name we give to force times time. And if you don't want to remember another physics term, don't. It's, you know, if you would rather go here, P initial is equal to P final, except when it's not. And it's not when there's a force times a time. Now, it's important to note that this is a vector equation, unlike energy, which is just a number. The direction of momentum and the direction of this force here matter. And so the first thing you do when you're using this equation is set up a coordinate system and stay true to it. And that's where the minus sign comes in when you're scraping across the pavement. If I'm going at some velocity to the right, by saying this is positive, I've chosen a coordinate system. The direction I'm going is the positive direction. Well, the friction force is going to fight that motion, so it must be pushing in the opposite direction. for some time, and then I stop. And so that,
So, there was a problem on the practice exam, the first one, the multiple choice. That like talks about this guy dumping off building on grass and onto
Yes.
concrete. Can you explain that and how?
I would love to. That's a very good problem. Ken Taylor is a friend of mine who helped me teach, a wonderful teacher. He also fixes anything that breaks. So I thanked him for that by throwing him off a building. Now, the issue here is that the impulse is the name we give the force times the time. And it changes the momentum. But if Ken has a certain speed right before he lands, he has a certain momentum. And when he stops, he's gonna have a momentum of zero, whether he lands on concrete or whether he lands on grass. His change in momentum is gonna be what it's gonna be. You know, likewise, if you're going down the road at 30 miles an hour and you hit a big oak tree, your change of momentum is fixed. But that doesn't mean the force has to be fixed, because the impulse is the combination. So I can have an impulse that is either a big force times a little time. That's like just hitting the dashboard, or I can have a little force for a big time. So this is going to be like landing on concrete, and this is going to be landing on the grass. People got this problem wrong because they were answering a different question. They were asking themselves, which is going to hurt more? Well, clearly the concrete, the force is much bigger. But the impulse, the combination of the force times the time, that's the same. He had a certain momentum, it went to zero. The change in momentum is the impulse. Okay. So this question was more semantics. Do you know the difference between impulse and owie? Okay. You look troubled.
I'm processing because I didn't read the problem and then now I'm reading it.
Okay.
But
The statement he has not heard in either case is just flatly bogus. I mean, clearly he's gonna get hurt in one of those cases. Yes, sir.
In the sample exams, number 7, question about a guy, and there's a ball at the end of the frame, asking about work being done in one revolution. There was another one like that, and practice exam, and it was 0 both times.
Yes.
So I was just wondering.
Yes. The reason for that is that Derek has a really interesting definition.
No, gross.
It's positive force times the displacement if those two are in the same direction. It's minus force times the distance if those are in opposite directions. And it's 0 if they are perpendicular to each other. Now, if anything is going in a circle, we learned in the second tutorial at the beginning of this semester that the motion had to be tangent to the circle, but the acceleration had to be towards the center of the circle. And those are perpendicular to each other. Well, the force that's causing this acceleration has to be in the same direction as the acceleration. So that means that the force is going to be perpendicular to the displacement, what movement it has. And so that puts it into this category here. Okay. So if you think about, you know, being on a skateboard, if I push behind you, you speed up. If I push in front of you, you slow down. But if I just push to the side, you don't speed up or slow down. Right. That answer for you?
That first problem we did with the roller coaster, can you help us with part C where he shoots up into the air?
Oh, okay. When he shoots up into the air, we have we want to find the maximum height. Well, that's going to be an energy problem. So if I go energy initial plus Verk is equal to energy final. If I choose point B to be my initial and use the top where he turns around and falls down as the final, there's no Verk being done in between. The friction happened before point B. And that's why I chose B instead of A as my initial, just to make things easier for myself. Well, I found when I was doing that problem before, I found that the energy initially was 43. At the top at B, it was 43,000 joules. So if I go back here and say 43,000 joules has to equal the energy at the top. Focus. There we go. Okay. So I asked myself at that turnaround point, the same three questions. Is anything with mass moving? Oh, you got to stop to turn around. Is anything up off the floor? Oh, yeah. And are any springs stretched or compressed? Not anymore. So this is going to be the 250 kilograms times G, 10 newtons for each kilogram, times H at C. And that will give you the height.
My question has to do a bit with the momentum chart with elastic, inelastic, and maximally inelastic. So I understand about like how momentum's conserved in each one and how elastic is the one where the energy is conserved. But my question has to do with understand some of the problems they'll give us an equation or will have us solve it out, but how we would solve to know if it's elastic or not.
Whether it's elastic or not?
Yeah.
Well, if you solve for the initial and final velocities of the objects, then I would just say, let's say I had two blocks A and B. And they come in and collide, and then I know that they come out, something happens. I just have to do a calculation and say 1/2 m of A times V initial A squared plus 1/2 m of B times V initial B squared And then I do the same thing after the collision. 1/2 MA times V final of A squared plus 1/2 MB V final of B squared. If I get the same number for those two calculations, it was elastic. If I get different numbers, it was inelastic. There's no, I know that's messy. I know that's an extra calculation and you already thought you were done because you did the collision problem. But there's no easy way around it, only through it. You can look at a collision and tell when it's maximally inelastic. They stick together. Oh, my goodness, those are stuck. But you can't tell elastic or inelastic without doing that calculation. Does that answer your question?
You know, that answers that one.
What?
Yeah, that answers it, yeah.
So there's no way to find or mathematically if it's maximally inelastic, right? You have to be given that in the problem, so to speak.
No, if I work out my collision and I find that cart A and cart B are both going at -4 meters per second, they're stuck.
Got it.
Yeah.
Stick together.
In another sample exam, the third one. In problem one, when the blocks stick together in your sample key, you found the velocity.
Oh, from there. It was the same setup before the collision. We just changed what happened after the collision. And so when I take the momentum of this, which was 50 to the right, and the momentum of that, which was 90 to the left, and add them together, it's -40. It's the same starting situation. I didn't have to change that number. Yes.
Can you go over Galilean transformations? The Galilean,
Oh, Galilean transformations. Just point of view, okay? When you're in a situation where you're asked about a Galilean transformation, imagine yourself in a car. And when you're going down the road at 60 miles an hour, the steering wheel looks like it's not moving. That makes it easier to drive. So from my point of view, the velocity of that steering wheel is 0. But the trees on the side of the road look like they're going towards me at 60 miles an hour. And so that's a Galilean transformation into the frame of reference of the driver. Everything in the car looks stationary. Everything that's growing on the side of the road looks like it's coming towards me. Now, if I'm going 60 miles down the road and there's a police car coming towards me at 80 miles an hour, again, my steering wheel looks like it's not moving. But that police car looks like it's coming at me at 140 miles an hour. So that's all it is. And I deeply, deeply apologize that when I finished writing the exam and I was feeling good about all the questions, I realized that I didn't have any questions about Galilean transformations. And I wanted to go back and change that, but I was too lazy.
okay.
Oh, no.
Yes.
Again,
You know, it wouldn't, if it were on the exam, you'd get it right. I mean, it's not that hard. You just make it sound scary because of the name.
On practice exam number 1, can you go over problem 8 on the multiple choice?
Oh, yes, yes, yes. Okay. So we have Actually, I turned this. Right here. There we go. So, we know that this block is lowered by 4 meters. Well, this tension force is pulling up in that direction. And the key here is that we're looking for the change in kinetic energy. We don't want to know what the kinetic energy is to begin with or what it is to end with. All we care about is how much did it change. Now, there's a whole class of these problems. You had 2 in your homework where instead of using this formula, E initial plus Verk is equal to E final. You know, to use that, I need to know what the initial energy is, the final energy. I don't know, and I don't want to know. And so what I do is I subtract the initial from both sides, and I get Verk is equal to E final minus E initial, or the change in mechanical energy. Now, just like your bank account, if you have a savings account and a checking account, the change in your money is going to be whatever change you had during the month in your savings account, plus whatever change you had in your checking account. And so I can write that as Verk is equal to the change in the kinetic energy account, that's my savings account, plus the gravitational account, that's my checking account, savings checking, okay? Well, this is what I'm looking for. If I knew what these other 2 things were, easy peasy, right? Well, let's look at the Verk. The force is pulling up at 65 newtons while it's moving down 4 meters. Is that going to be positive or negative Verk? Shout it out. We don't have a microphone. Negative. Yeah, the force is one way, the displacement's the other way. That's going to be negative, and it's going to be negative 65 times 4. That's going to be negative 260 joules. What about the change in gravitational energy as it lowers and gets closer to the center of the Earth? Is that going to be a positive change or a negative change? Negative, yeah. That energy bucket is draining. It's losing its capacity to do damage. And so in that case, it would be the change in gravitational potential energy would be mg change in height. So that's going to be 5 kilograms times 10 newtons for each kilogram times negative 4 meters. And so that's going to be a negative 200 joules. Well, what do I have to add to negative 200 to make it negative 260? Negative 60. And so the answer here is negative 60 joules. Well, how can that be, Greg? If you started from rest, how can you have a negative change in kinetic energy? How can you slow down from rest? You can't. I never said this thing started at rest. You just assumed that in your little mind. You went places you shouldn't have gone. Okay. Keep your mind where it's supposed to be.
Well, I understand this and it makes sense, but just thinking about it, kinetic energy is 1/2 speed. What if it's going at constant speed? How does that change?
Oh, it's not. It's slowing down. And you can see that by a free body diagram. if I draw a free body diagram for this, I have, this tension force is 65 newtons up. The weight force is going to be 50 newtons down. That diagram screams net force up, does it not? And that means that the acceleration is up and the motion is down. And so if the acceleration is this way and the velocity is that way, it's slowing down.
In this situation, could you not just take the net force and multiply it by the distance? Right, wouldn't the net force be 15 times 4?
No, that would, oh, I see what you're saying. That would give you the right answer. But it's a dangerous precedence because what you're doing is calculating the work done by the gravitational force. And we've always agreed to put the Earth into our system so that we never calculate. You do get the right answer that way.
Right, okay, just making sure.
And you'll always get the right answer that way, but it will hurt my soul. And I will weep.
I want that.
Right. Right to sleep. Good? No, we're not.
I have a question about 2D like motion with momentum,
With what?
like 2D motion with momentum.
Oh, yes.
Like how to use the components to find the final momentum, like when they stick together.
Okay. Are you referring to that tutorial homework problem where they stick together? Move out?
Yeah, pretty much.
Okay, so in that problem, we were told. You mean that problem there?
Yeah.
So we were told that A had an initial velocity that was 6 squares, 1, 2, 3, 4, 5, 6 squares down, and 9 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9 squares to the right. So it's the initial.
Can you pull it down a little bit? Thank you.
Thank you. So that was the velocity. And so that's, each one of these squares is 0.1 meters per second. So that's 0.6 and that's 0.9. Okay. Now, afterwards, if I look at A final, its velocity was still 6 down. But now it was only 3 over. So that'd be 0.6. And that would be 0.3. Now, what we really care about is momentum, because momentum's what stays the same during a collision. And so the mass of A is 5 kilograms. I have to multiply mass times velocity to get my momentum. And so what I'm going to get here is 3 franci down and 4 franci, 4.5 franci to the right.
Can you switch it?
That look right? Okay, Now afterwards, I'm gonna have 3 franci down and 1.5 franci to the right. Now, those are different. And the difference we call the delta P for A. And it's what I would have to add to the initial to get the final. Well, in the y direction, I don't have to add anything. That didn't change. But if I want to change 4.5 to the right to only 1.5 to the right, what do I have to add? What change do I have to add? Well, 3 to the left. So this is going to be 3 franci left. Well, what does the change have to be for B? Well, here's the beautiful thing. And that is that in a collision, whatever change A has, B has exactly the same change with a minus sign. Okay? If we turn off the lights and we shut those doors, we leave the lights off for 2 minutes. And then we turn the lights back on, and I have $100 more than I had when we turned off the lights. One of you has $100 less. It's some game. Okay, if the change for the group is 0, the doors were shut, one of us had to lose $100. Okay, so this is going to be the change in B is going to be 3 franci, right? Oh, yes.
Why is it 3?
For A or for B?
For A.
For A, if I had $4.50 and then I only have 1.5, the change is -3. Yeah, or 3 to the left is what that minus sign means. And the reason B has 3 is because A had 3. Yeah. Now, if I know the change in B is 3 to the left, I'm sorry, 3 to the right, I know what the final momentum is for B. I was given the final velocity for B because they stuck together. It has the same final velocity as A. So let's look at B now. B remember, the final velocity was 1, 2, 3, 4, 5, 2, 3, 5, 6 squares down and 3 squares across. Meters per second. And if I look at the total momentum of them together, the mass of A plus the mass of B, well, this was 5 kilograms and this was 3 kilograms. That's going to be 8 kilograms. So that means the total momentum is just going to be 8 kilograms times this velocity. Well, that's going to be 4.8 franci down and 2.4 franci that way. Well, remember what A had. A had, let's go back, 3 franci down and 1.5 franci to the right. Well, this is what A had afterwards. This is what A and B had afterwards. Well, whatever part of this is not from A has to be from B. Okay, so that means for B, A had 3, the total had 4.8, so that's going to be 1.8 down. And A had 1.5 to the right, B had 2.4, that's gonna be 0.9 to the right. So now I know what B had to begin with. Oh, sorry. You know, if we find out that without the microphone, the recording is just a complete us, you people are the winners because no one else is gonna be able to stand the review. You'll have to teach them. what to know about it.
Can you go over number nine?
Sorry, it's Grand Labyrinth.
Some number 9. Oh, sure.
I'd rather get the answer now that you-
Unfortunately, I've goobered that page already. But it's released from a height. And it collides with that 2 kilogram block at its lowest point, and it stops. But the block takes off at 5 meters per second after the collision. And we want to find out what H is. So if we look at the swing, starts out some distance H. Oh, draw that very well. Let's start by drawing the floor. So it comes down from some distance H. And it's going some speed. And the block is not moving. And then after the collision, we've got the bob, the ball, not moving. And the block moving at 5 meters per second. And remember, this is 1 kilogram and this is 2 kilograms. Well, during a collision, momentum's conserved. So here I had 1 kilogram moving at V, we'll call it V initial. And I had 2 kilograms not moving. I just wasted ink. Down here, we had 1 kilogram not moving, wasted more ink, plus 2 kilograms moving at 5 meters per second. Since these have to be equal to each other, that means 1 kilogram times V initial is equal to 2 kilograms times 5 meters per second. And that means V initial has to be 10 meters per second. So far, so good?
Why is your V initial not 0 if the ball is being released?
Oh, V initial's not here.
Oh, it's right before
And
the collision.
I'm talking about the collision.
Okay.
At the beginning of the collision, the end of the collision,
Okay.
okay? And so this is, we're looking at this part here where it's smack on the block.
Are we assuming that the ball just stops moving once it hits the block?
We're told that in the problem.
Okay, okay,
It comes down, hits the block, and it stops.
gotcha.
Yeah.
In two, it's said it's the problem where the pendulum swings and then it stops. Would that be useful?
That is a useful problem, but it's no different than this problem. So it's just a different starting and stopping point. So now let's find H. We know that if I call that point A and this point B, I know that the energy at A plus Verk done between A and B is equal to the energy at B. But Tarzan swings don't do any Verk. And so this Verk would be 0. At A, all of my energy is potential. That's an A. I spelled it with a B, but it's an A. At B, all of my energy is kinetic. And the masses cancel. And so what I get is that H at A is equal to BB squared over 2G. That's going to be 10 squared over 20, and that's going to be 5 meters. Okay.
So how do you solve the problem if you don't know that the ball comes to a stop?
You could.
Okay.
You would have to be given some information about that ball's velocity. But I could have said it bounced back at, say, 1 meter per second, and that would give you a different answer for the height. Yeah. But first of all, you have to find out what that energy is at the bottom before you can find information about the top. Now, with your problem of the pendulum going wrapping around, you just put potential energy at the start, and then at the top of the little circle, it had 2 flavors of energy. It had kinetic energy and still a little bit of potential energy, and we set those equal to each other. And the reason we did that with the nail is, again, we wanted a problem that was going in a circle so that we could do that review of circular motion and have to do the centripetal acceleration.
When solving for power and we're not given like the force for the equation, could we like solve for the impulse's force and then use that to apply for the?
No. Power is inherently connected to energy, not momentum. Has nothing to do with momentum or impulse. And so what you want to do when you're calculating the power is either figure out how much Verk was done or how much the energy changed. And those are the same thing, because Verk is what changes energy. And then just divide by how many seconds it took to make that change. And that's the power. But stay away from momentum, stay away from impulse when you're dealing with a power problem. They didn't clean up that. Well, they did. They took the microphone. They cleaned us out. Okay, we're out of time. We have class tomorrow. I will be in my office Friday. You're welcome to call me. I have my cell phone number. Call me on the weekend. My office is in the Science Center, across the hall from the health center. 355.
It's one of those review.
406 581 3783. It's all in the syllabus.
Just like.
I know, I just saw you like.
So we survived 2 years ago. This class. So.
That's a net down. Net force is 2 things. It's a weight Because it's both the weight and the normal that give you.
2006.
Wow, thank you.
You're welcome. Stay out of trouble. Stop this.